Welcome everybody to Sustainable River Basin Management, and we will start today our Module 2. The contents of our Module 2 will be about natural water resources, and we will follow the topics hydrological cycle, catchment terminology, we will cover water balance, water availability, and river basin management. You should get hold of some basic literature on natural water resources. I've recommended some here. You can choose any other. If you already have literature at home, you can make use of those. Let's start with the first question, a question that you may have asked as a child already. Where does our water come from? And it's also one of the oldest questions of humankind, which was tackled by scientists and philosophers over centuries of years. The first documented explanation of the hydrological cycle, which introduces the concept of the meteorological water cycle, is available by a Greek, the Greek Xenophanes, about 580 years before our time. And he also introduced the idea that our overall amount of water is constant, so that we are working with a water cycle and a constant amount of water. This theory is considered as being valid today and is our working theory up to now. Where does water occur and what is water in general? Water exists on Earth in the form of solids, as ice, in liquid format, as you know, and gas or water vapor. And it occurs as fresh water, as salt water, as glaciers, in oceans, rivers, lakes, clouds, and rain. What is relevant for us for water usage is the freshwater component of it. Let us introduce the term hydrosphere here. What we mean by hydrosphere is a continuous layer of water in liquid, solid, or gaseous state. This continuous layer we call hydrosphere of the Earth. Also important to introduce right in the beginning is that water is in a frequent state of change. That means what we measure and observe today will be different the next moment we measure or observe it again. And this is also one of the challenges of water management. So what it means is, or what you are also aware of, let's just give an example. The surface water will evaporate, that clouds will condensate, eventually will precipitate as rainfall or snowfall, and that rainfall will reach the ground and possibly infiltrate and become groundwater, and so on. Now let's just reflect upon the origin of our hydrosphere. And there are two concepts of how water is formed. The first one is the meteorological water, and the second, the so-called juvenile water. The meteorological water is water that is currently part of our water cycle, whereas the juvenile water is water that is formed during magmatism and released through volcanism, the process. And the assumption is that it has not been part of the water cycle yet. That's why it's juvenile. How is this possible? Let's just look into a brief example. You may have heard about plate tectonics, or continental plates and our oceanic plates. And those plates shift around permanently or constantly. And at the borders of such plates, a denser plate like the oceanic plate may be pushed underneath the lighter or less dense plate, the continental plate, and in that way any water that was incorporated into a sediment pack here, just like a sediment layer at the bottom of our oceans, gets subducted and incorporated into our magma and incorporated into a new phase of magmatism. In the same way, water can come back to and join our water cycle through volcanic activity. And those are small amounts on both sides, and that's why we can still say that our overall water amount remains constant. What we also have to state, if you think about this model here, that most of our water is not truly juvenile, but it has to be called recycled water. Now, we've been talking about cycling and water cycles already. Let's just define that term. We can say water cycle, but we can also use the term hydrological cycle. It's one and the same, and it expresses the circulation and conservation of water on Earth. It is basically a conceptual model which depicts processes at various scales. It can be used at global scale, regional, or even local scale. And it describes two things: the storage and movement of water between our spheres. And we differentiate between the biosphere, the atmosphere, lithosphere, and the hydrosphere. We have talked about the hydrosphere already, and we will be coming back to the other spheres throughout the course. And the same conceptual model can be used to describe energy fluxes. Now, let's just take a look into the water cycle in more detail. This picture here shows us the water cycle. It shows us the sun, a very, very important part of the water cycle, and it shows us the oceans, or part of the ocean, and it shows us the land surface here. And then we have clouds and arrows showing us our movement of water particles. And what we can see is that we can look at this as a large cycle, but we can also look into smaller cycles, just a cycle between the ocean and the land surface, or cycles between different parts of land surfaces. Now, what keeps all this moving is our solar radiation. Our sun is the engine of this entire movement. What you can see is where our major portions of water recycling or water cycling is taking place. We can see is that groundwater is a minor source here, and the major part that participates quickly in our water cycle are surface components. Now, important here is that the balance between evaporation processes, evaporation has to take place, a water supply has to take place to be able to have rainfall taking place over other parts of the water cycle. So there must be a balance between those two. And essentially this process starts from the large stock that we have, which is our ocean. We have minor stocks, and in countries which are landlocked and very distant from oceans, very often this the evaporation from land may play a major role, or even the only important role of water supply in this part of a water cycle. We'll come back to this at a later stage. Now, let's move away from this a conceptual model of the water cycle and try to look at it as a system, from a systems perspective. And let's define system first. The system is a universe of variables, and those variables could be elements or properties which can be differentiated from its surrounding environment. And hydrological systems could be, for example, the global water budget. It could be an ocean or continents. It could be a river basin. It could be a part of a river basin. For instance, if you just want to understand what happens between the source of the water and a dam, or between a water abstraction point and a delta. It could be a groundwater catchment, it could be an urban water supply area, or it could be any other reference or research site of interest. All of those we can define as systems or subsystems. Now, let's look into the components of such systems in general, and let's apply this to our hydrological systems. A very important component are our storage compartments. We can use as alternative terms, and you can see this in the literature also, a reservoir or a stock if you look into financial applications. And such a reservoir could be, for instance, our clouds, our rainfall. It could be a lake, it could be an aquifer as examples. And then we have a very important additional component, which is so-called a feedback loop. Those can be positive, they could be negative, or they could be self-reinforcing, or they could be positive self-reinforcing or negative self-reinforcing. And those are components, as you can see, which are not actually as such part of what we have seen from our water cycle. Those are inputs to our system, such as, for example, the change in albedo due to deforestation, the heat island effect in urban areas, or, for example, radioactive decay of aerosols, as examples. The third important component of systems is the flow, the fluxes that take place, and those are processes. And a process always means a modification of a variable of the system over time. And this can be through change of location, or it could be through change of properties. For example, in the case of the hydrology, evaporation or condensation, precipitation, percolation, but it could also be contaminant transport or contamination pollution processes. And then we have a fourth component of systems, which is usually called communication or information. And this is in hydrological systems often referred to as a system memory. We'll come back to all those components throughout our lecture again. Now, let's look into the storages or the stock that I just mentioned before, and the fluxes, the flows that take place in between them. The arrows already shown here show us the fluxes. Now, we've seen from our hydrological cycle that we essentially move water particles through three different spaces, through our atmosphere, through our land surface, the terrestrial part, and to our maritime or ocean parts. So the major parts. And when we look into the terrestrial, it becomes very complex, and it can be even more complex than what I'm showing here, that water actually moves through vegetation, soil moisture, it's in our rivers and lakes, wetlands, and also in groundwater. And in addition, in a solid or long-term changing state in glaciers. And then we have all of this interacting with each other at various stages, and after all joining at any time again our oceans, faster or slower in the process. And any feedback takes place between our atmosphere and our terrestrial part, and the oceans and the atmosphere, but it does not take place from the oceans to our terrestrial or land part. Now, if you want to get an idea of the size of our storages, we can see the numbers that I've just clicked in to this presentation, and we can see that the oceans are by far our largest stock. This is overall the source of all our water. And the smallest, or a comparatively fairly small stock is our atmosphere. And this suggests that any water that is moved through our water cycle has a very short residence time in the atmosphere. What we can also see here is that major storages, major stocks are our groundwater reservoirs and our glaciers. Now keep in mind that with climate change, some of this is changing and our glaciers are becoming smaller, so this means that this number also will be changing. It will become smaller and this water will join our rivers, groundwater, probably end up in our oceans, and as such be part of our water cycle again. The number in meters that you can see next to the storage size indicates is a different expression of the same. It simply tells us the distribution. If we would distribute those amounts as a uniform layer above the entire surface of the Earth, how it would look like. If you can imagine, or just imagine a sandwich with different layers, and then we would have the oceans as the thickest sandwich layer, and followed by groundwater and glaciers and so on as various smaller layers of that. Now, I mentioned residence times already because we can see it already from storage size and the relevance and importance of some of our storages. There's an interesting figure that I want to show you, which summarizes all this. We have here our different water stocks, different water storages here, and then we have here our years, and this starts from 0 to about 10,000 years. And what we can see is that the biospheric water, means water stored in living matter, is fairly short, very short-lived. So this water participates very quickly in the water cycle, and the same applies to our atmospheric water. It comes to about 10 days of water that from evaporating to becoming rainfall again, it only remains about 10 days in the atmosphere. And you can also see that the longest, looking into freshwater components, is our groundwater. Groundwater has a very long residence time in our as a storage in the aquifers, which can reach about 10,000 years. So this is important from a management perspective, from a water quality and water quantity, water availability perspective. And we'll come back to this at a later stage. The other important factor besides the residence time is the spatial and temporal scale of these fluxes, which I want to demonstrate you as well here. This is a graph that shows us two dimensions. One is the distance in terms of geographical range, and this is year in terms of spatial range. In terms of temporal range, I'm sorry. And then you have individual events. Those dots are all different events clustered as per what type of event, and the distance it impacted on and the temporal scale it took on. And what we can see is that the weather events, the daily weather records that we observe all occur within the very short-term spatial and temporal scale window, whereas the surface water events, like flood events, like storm flows, overland flows, occur in a time window of hours to days and within a range of around a few kilometers, up to about 10 kilometers. And those are the events that form or shape our climate variability, our climate pattern in our respective region. And then we have a large cloud of events which are all related to groundwater interactions, to groundwater events in different types of aquifers under different conditions, saturated, unsaturated, which take place over a short to a very, very long period of time, over short or small geographical ranges to very large geographical ranges. And those we usually shape our long-term, our lagged responses on water, on the water cycle, and on climate as such. That is what we also call climate, as you remember from our previous class. At this point, I want to stop, and I see you again for the next class.